Artificial General Intelligence, or AGI, represents the pinnacle of theoretical computing. It is a form of AI capable of learning, understanding, and applying knowledge across any intellectual task at a level equal to or exceeding human capability. Unlike standard AI, AGI requires a synthesis of disparate skills, from visual perception and navigation to creativity and emotional engagement. It is not just about computing power. It is about holistic integration. While narrow AI excels at predefined single-domain tasks, AGI is characterized by its adaptability. It is a system designed to handle evolving, complex, and open-ended objectives without being hard-coded for every scenario. Most AI today is narrow AI. It is highly efficient but designed for specific predefined tasks like translating languages or recognizing images. By contrast, Artificial General Intelligence, or AGI, represents a shift toward true versatility. It is not limited to a single script or task. AGI possesses the ability to handle novel, unseen problems by applying knowledge across different domains, without needing to be pre-programmed for each individual challenge. The core characteristic of AGI is cross-domain reasoning, the ability to transfer knowledge across unrelated fields. If an AGI learns physics, it can apply those laws to solve problems in cellular biology or structural architecture. Unlike narrow AI, which struggles outside its training data, AGI creates logical bridges between these domains. In 2026, we have moved beyond simple chatbot interfaces. Traditional models offer linear, single-turn responses. In contrast, Agentic AI systems display true agency. These systems independently set sub-goals and navigate complex, open-ended workflows to solve problems without requiring constant human guidance. At the heart of this shift is a recursive reasoning framework. The agent plans, evaluates its own progress, and observes outcomes in a cyclical, iterative process. By integrating memory modules and external tools, these agents transform from passive calculators into proactive partners capable of managing intricate multi-step tasks. The evolution of AGI marks a shift from simple pattern matching, known as System 1 thinking, towards System 2 deliberative reasoning. Modern models now act as deliberative systems. They simulate outcomes, evaluate plans against constraints, and perform self-reflection before committing to an answer. This workflow demonstrates the reflection pattern. By looping between generation and analysis, the system identifies errors, refines its reasoning, and iteratively improves the final output. This transition is fundamental. It empowers AI to solve complex, novel problems that require deep logic rather than just statistical inference. To function as reliable, autonomous employees, AGI systems must maintain context over long periods. This architecture illustrates how sensory inputs and short-term memory integrate into a long-term system that stores project histories and organizational knowledge. At a structural level, these systems use mechanisms like gates to manage information flow. By encoding past experiences into weights and knowledge bases, the model evolves its goal-setting capabilities over time. Ultimately, persistent memory allows an AGI to move beyond task execution. It becomes a system that remembers what it has learned, understands the progress of complex project histories, and effectively manages evolving goals autonomously. To bridge the gap between digital intelligence and physical action, researchers are shifting from standard autoregressive models to world models. A world model simulates physical laws and spatial relationships. It doesn't just predict the next token, it predicts how an action changes the physical state of the environment. This enables high-fidelity simulations where robots learn movement patterns before ever interacting with the real world. While early models struggled with spatial tasks, modern world models are drastically improving in object manipulation and physical navigation. By integrating these world models into robotic hardware, AI is finally attaining the dexterity required to operate in the physical world. In the 2026 agentic workspace, AI has moved beyond simple code suggestions. Autonomous agents now manage the entire software development lifecycle, writing, testing, debugging, and deploying code without needing constant human intervention. The process follows a comprehensive flow: requirements, design, implementation, testing, deployment, and maintenance. AI agents assist in every stage by ensuring consistency and catching logic errors. The core architecture involves a foundation agentic model that integrates directly with code repositories. It processes business rules and personalization constraints, then autonomously executes deployment within cloud environments like Kubernetes. The result is a self-correcting development pipeline where the system adapts to changes in real time. Human engineers shift their focus from repetitive manual labor to high-level architectural oversight and strategic innovation. AGI frameworks are transforming materials science by automating the discovery of new battery chemistries and drug candidates. These systems utilize a 10-step pipeline, starting from target identification and moving through simulation and feature selection. By using architectures like PaNet, models can predict electronic properties of molecules, dramatically narrowing down the chemical space. Machine learning workflows like these allow agents to sample and refine compounds iteratively, accelerating discovery by millions of simulated experiments. This unprecedented speed allows us to solve complex chemical problems that were once considered impossible for human-only research teams. As AGI systems achieve human-level performance, the focus shifts from raw competence to alignment. We must ensure an AGI's goals remain tethered to human safety and ethics. Alignment is not a single rule, but a complex framework. It covers benefits, safety, explainability, data privacy, and continuous governance. The alignment frontier is essentially the digital scale of justice. It requires fusing rapid technological development with rigorous human-centric constraints. Constitutional AI is a framework where developers encode specific human constraints that the model is mathematically forced to adhere to, acting as a safeguard for superintelligent outputs. As shown here, guardrails filter inputs and outputs, ensuring the model's reasoning stays within the boundaries of the Constitution defined by human values. The model is trained through an iterative process of critique and revision, where the constitutional constraints refine the model's preference patterns. Ultimately, formal verification methods aim to mathematically prove that these constraints remain intact, providing a foundation for safer, superintelligent systems. In 2026, the rapid advancement of intelligence capabilities has prompted nations to formalize international AI compacts. These compacts establish shared safety standards, ensuring that progress does not outpace the ability to manage existential risks. Major powers now recognize Tier 1 AGI as a critical strategic resource, vital to national security and future economic stability. This has led to stringent export controls on specialized hardware and high-end training clusters, alongside mandatory state oversight of large-scale training runs. By mid-2026, agentic AI workflows have fundamentally transformed the global economy. In G7 nations, data shows that between 30 to 40% of non-manual labor tasks are now fully automated. This transition has unlocked a massive surge in corporate productivity. Machines now handle complex scheduling, data analysis, and report generation autonomously. However, this rapid shift has triggered profound changes in the labor market, necessitating new strategies for job transitions and workforce development. As these systems continue to evolve, the challenge lies in balancing this newfound efficiency with the social and economic needs of the human workforce. Experts debate how AGI will emerge. Some fear a hard takeoff or singularity, where intelligence explodes instantly. However, most now favor the soft takeoff theory. In a soft takeoff, AGI integrates slowly into global infrastructure. This allows societies to adapt, regulate, and align the technology as it matures, avoiding a sudden societal shock. Unlike theoretical explosions, real-world deployment faces chasms, regulatory, economic, and infrastructure barriers. These constraints naturally slow the transition, turning a potential singularity into a manageable, multi-decade transformation. By integrating AGI gradually, we ensure that as intelligence grows, so does our ability to manage its impact on the world. The goal of AGI is not to replace human contribution, but to act as a powerful force multiplier. By acting as intelligent digital agents, AGI systems allow individuals to orchestrate complex tasks at a massive scale. You become the conductor, defining objectives while the system handles the execution, monitoring, and iterative adjustment. This transition turns professional work into a process of orchestration, where human creativity and agency are augmented by artificial capability. The future of work is a collaboration, not a competition. The rapid rise of AGI has led to significant shifts in the labor market. Approximately 300 million full-time jobs globally face potential automation, particularly in administrative and office sectors. Governments are now exploring policies like universal basic compute. This framework proposes taxing major AGI firms to fund public dividends. It aims to distribute compute power and financial equity to citizens, fostering a more inclusive AI-driven economy. Finally, policy focus has moved toward extensive job retraining. Preparing the workforce involves teaching humans how to orchestrate agentic systems, manage ethics, and lead in a world where AGI handles the tactical execution of complex tasks. As AI capabilities approach human levels, we face a critical philosophical question regarding the future of intelligence. Does the value of an advanced system reside in its raw processing power, the ability to solve any task? Or does its true importance lie in its perfect alignment with human values and goals? This balance is the frontier of modern research. It asks whether we value the tool's power or its purpose. By mid-2026, the artificial intelligence landscape has fundamentally shifted. We have moved past the era of standard chatbots that simply predict the next word. We are now in the reasoning explosion era. Modern systems no longer just write. They deliberate, iterate, and verify their logic before outputting a result. The primary shift is from writing to solving. As seen in complex puzzle-solving architectures, AI agents now utilize theorem provers and iterative feedback loops. The progress of 2026 is defined by this transition to System 2 architecture. Intelligence is no longer just about information. It is about the reliability of the reasoning chain. AGI is not a sudden finish line. It is an ongoing, evolving process of development. We are steadily moving toward a future where machine intelligence serves as a critical tool for human advancement. The evolution of these systems shifts our focus from simply increasing raw compute power to fostering purpose-driven, highly capable intelligence. By aligning these tools with our values, we create the potential to solve our most long-standing and complex global challenges. Ultimately, the true value of AGI will be measured not just by its capability, but by how well it empowers humanity to build a more sustainable and prosperous future.